You're cruising at 35,000 feet. You look out the window and see another aircraft in the distance, also at cruise altitude. It's miles away, but it's there. And you think, with thousands of planes in the sky at any moment, how do they avoid crashing into each other? There are no traffic lights, no lane markings, no stop signs. At 500 mph, visual scanning is useless. By the time you see another plane, it's too late to react. So how does the system work? The answer involves layers of technology, strict rules, and constant communication between aircraft and ground controllers. Let me explain exactly how planes avoid mid-air collisions, and why the safety record is so remarkably good despite the apparent chaos. First, let's frame the problem. On any given day, there are roughly 100,000 to 200,000 commercial flights worldwide. At peak times, over 10,000 aircraft are airborne simultaneously. They're flying at different altitudes, speeds, and directions. Some are climbing, some descending, some cruising. The airspace is three-dimensional, crowded, and constantly changing. Yet mid-air collisions are extraordinarily rare. In commercial aviation, they happen roughly once every few years globally, and when they do, it's almost always due to multiple system failures or human errors. The system works. But how? Now here's the scale. Aircraft don't fly randomly through the sky. They follow specific routes called airways, which are like highways in the sky. These airways are defined by geographic coordinates and navigation beacons. Aircraft file flight plans before departure, specifying which airways they'll use, what altitude they'll fly at, and what speed they'll maintain. Air traffic controllers approve these flight plans and monitor aircraft as they fly. This creates predictable, organized traffic flow. But airways alone aren't enough. The key is altitude separation. Aircraft flying in opposite directions are assigned different altitudes. In most airspace, eastbound flights fly at odd thousands of feet, 31,000, 33,000, 35,000. Westbound flights fly at even thousands, 32,000, 34,000, 36,000. This is a global standard. It ensures that aircraft flying toward each other are vertically separated by at least 1,000 feet, usually 2,000 feet. At cruise speeds, 1,000 feet of vertical separation is more than enough to prevent collision. Let's destroy the biggest misconception immediately. Pilots do not avoid other aircraft by looking out the window. At cruise altitude and speed, visual detection is nearly impossible and completely unreliable. By the time you see another aircraft, you're already too close. The system relies on technology and communication, not human vision. Now let's break down the mechanics. Every commercial aircraft is equipped with a transponder. This device continuously broadcasts the aircraft's identity, altitude, speed, and position. Air traffic control radar stations receive these signals and display aircraft positions on controllers' screens. Controllers monitor the airspace, ensuring aircraft maintain safe separation. If two aircraft are on a collision course, the controller issues instructions to one or both, directing them to change altitude, heading, or speed. But air traffic control is just one layer. The second layer is TCAS, the Traffic Collision Avoidance System. TCAS is installed on nearly all commercial aircraft. It's an automated system that operates independently of air traffic control. TCAS continuously monitors transponder signals from nearby aircraft. If it detects another aircraft on a potential collision course, it calculates the time to closest approach. If that time drops below a certain threshold, TCAS issues an alert. There are two types of alerts. A traffic advisory, or TA, warns pilots that another aircraft is nearby and could become a threat. It's informational. Pilots acknowledge it but don't necessarily take action. A resolution advisory, or RA, is urgent. It means collision is imminent unless action is taken. TCAS calculates the safest escape maneuver and commands the pilots, climb, climb, or descend, descend. Pilots are trained to follow TCAS RAs immediately, even if it conflicts with air traffic control instructions. Here's the brilliant part. TCAS systems on both aircraft communicate with each other. If one aircraft's TCAS says climb, the other says descend. They coordinate automatically to ensure the aircraft move apart, not toward each other. This happens in seconds, without human input. It's a purely automated collision avoidance system. Let's go deeper into the real-world application. TCAS has prevented countless collisions. There are documented cases where TCAS issued RAs seconds before impact. Pilots followed the commands, and the aircraft passed within hundreds of feet of each other instead of colliding. In some cases, passengers saw the other aircraft flash past the window. Without TCAS, those would have been fatal collisions. But TCAS isn't perfect. It requires both aircraft to have working transponders. If one aircraft's transponder is off or malfunctioning, TCAS can't detect it. This is rare in commercial aviation, but it can happen with military aircraft or small general aviation planes that aren't required to have transponders in all airspace. That's why other layers exist. Another layer is procedural separation. Air traffic controllers are trained to maintain minimum separation standards. In en route airspace, the standard is typically 5 nautical miles horizontally or 1,000 feet vertically. Controllers actively monitor aircraft positions and issue instructions to prevent violations. If separation is about to be lost, controllers intervene immediately. There's also altitude restrictions. Certain airspace regions have mandatory altitude assignments. Controllers don't allow aircraft to climb or descend freely. Every altitude change requires clearance. This prevents aircraft from accidentally entering another aircraft's flight level. Now, the edge case. What about areas with no radar coverage? Over oceans, remote regions, and polar areas, radar doesn't reach. Air traffic control can't see aircraft positions in real time. In these areas, procedural separation is used. Aircraft report their positions via radio or satellite communication at regular intervals. Controllers track them on paper or computer systems. Separation standards are larger, often 10 or 15 minutes of flying time, to account for uncertainty. This is less precise than radar separation, but it's still effective. Recently, ADS-B, Automatic Dependent Surveillance Broadcast, is replacing radar in many areas. ADS-B uses GPS to determine an aircraft's position and broadcasts it via transponder. Other aircraft and ground stations receive the signal. It's more accurate than radar and works globally, even over oceans. Most modern aircraft are ADS-B equipped. Let me address another misconception. Some people think pilots can see other aircraft on their navigation displays. Modern cockpits do have displays showing nearby traffic fed by TCAS and ADS-B. Pilots can see icons representing other aircraft, their altitude, and direction. But this is situational awareness, not collision avoidance. Pilots don't navigate by watching traffic displays. They follow assigned routes and altitudes. The displays supplement, they don't replace, the automated systems. There's also the human factor. Pilots are trained to maintain situational awareness. They listen to air traffic control, monitor TCAS, and cross-check their instruments. They know their altitude, speed, and heading at all times. If something seems wrong, they query controllers. Communication is constant. Here's another detail. In congested airspace near major airports, separation standards are tighter. Terminal Radar Approach Control, or TRACON, manages aircraft within about 40 miles of the airport. Separation is reduced to 3 miles horizontally, and controllers provide precise vectors, guiding aircraft step by step. The workload is intense. Controllers manage dozens of aircraft simultaneously, coordinating arrivals, departures, and overflights. Now let's talk about what happens when the system fails. Mid-air collisions have occurred. The most famous recent case is the 2002 Überlingen collision over Germany. A cargo plane and a passenger jet collided at 35,000 feet, killing 71 people. Investigation revealed that TCAS issued RAs to both aircraft. One crew followed the RA, the other followed conflicting instructions from air traffic control instead. The aircraft collided. The investigation concluded that if both crews had followed TCAS, the collision wouldn't have happened. This led to a rule change. TCAS RAs now take priority over controller instructions in all situations. There's also the 1996 Charkhi-Dadri collision in India, where a Saudi 747 and a Kazakh Il-76 collided, killing 349 people. Neither aircraft had TCAS. Altitude separation wasn't maintained due to pilot and controller errors. This tragedy accelerated the global mandate for TCAS on commercial aircraft. These incidents are tragic, but they're also instructive. They reveal how the system fails, and each failure leads to improvements. TCAS became mandatory. Training was updated. Procedures were refined. The result is that mid-air collisions are now extremely rare. So here's the conclusion. Aircraft avoid each other through a combination of procedural rules, altitude separation, air traffic control monitoring, and automated systems like TCAS. Pilots follow assigned routes and altitudes. Controllers ensure separation. TCAS provides a last line of defense if everything else fails. The system is layered, redundant, and constantly evolving. It's not perfect, but it's remarkably effective. Thousands of aircraft share the same sky every day, and the vast majority of flights complete without incident. To me, that's the beauty of the system. It's invisible to passengers. You don't see the transponders broadcasting, the controllers vectoring, or the TCAS systems calculating. You just see the sky. But behind that sky is a sophisticated network of technology and human coordination that keeps aircraft safely separated, flight after flight, day after day. There's another dimension worth exploring, the future of collision avoidance. Technology is advancing. Satellite-based surveillance is replacing ground radar. ADS-B is now global. The next step is automation. Some systems are being developed to allow aircraft to self-separate, adjusting their routes automatically based on traffic without controller input. This would reduce controller workload and improve efficiency, especially in congested airspace. There's also the issue of drones and uncrewed aircraft. As drones become more common, especially large commercial drones, they'll need to integrate into the airspace system. Many drones don't have transponders or TCAS. They're small, hard to detect on radar. Developing collision avoidance systems for mixed traffic, crewed and uncrewed, is a major challenge. Researchers are working on sense and avoid technology, where drones use cameras, radar, or LiDAR to detect and avoid obstacles, including other aircraft. Now let's consider the role of machine learning. AI is being tested to predict traffic conflicts before they develop. By analyzing flight plans, weather, and historical data, AI can identify potential issues hours in advance and suggest route adjustments. This proactive approach could further reduce collision risk. There's also a human factors angle. Controllers work in high-stress environments. They manage complex, dynamic situations. Fatigue, distraction, and workload all affect performance. Automation can help, but it can also introduce new risks. Over-reliance on automated systems can lead to complacency. If controllers stop actively monitoring because they trust the automation, they might miss critical situations. Training emphasizes this. Controllers are taught to use automation as a tool, not a crutch. Finally, consider the regulatory environment. Aviation authorities like the FAA, EASA, and ICAO set separation standards, equipment requirements, and procedures. These regulations are updated regularly based on accident investigations, technological advances, and operational experience. The global nature of aviation requires international coordination. What works in U.S. airspace must also work in European, Asian, and African airspace. Harmonizing rules across regions is challenging but essential. So the next time you're on a flight and you see another aircraft in the distance, you'll understand that its presence there isn't random or dangerous. It's the result of careful planning, constant monitoring, and automated systems working together to keep aircraft safely separated. The sky might look empty, but it's actually filled with invisible highways, altitude layers, and electronic signals, all coordinating to ensure that every flight reaches its destination without conflict. Now, if you've ever wondered how pilots know their exact position without GPS when flying over oceans, I've covered oceanic navigation in another video.